Hello there, everybody. My name is Alexander Savchenkov, and this is the Computer Programming is Easy series. Now, first of all, the name of the series is highly misleading because overall, as a profession, it's not any easier than anything else that requires knowledge and technical skill. However, getting into it is easy. In fact, astronomically easy. And that's what we're going to do in this series. So, if you want to just go straight into the code, I will leave a link below in the video that you can click to get to the end of the video where there, will be the rest of the videos that involve code that you can click on and start them instantly. However, if you want to learn the background of how computer logic works, then, well, follow me. So, first of all, you hear a lot about ones and zeros. And well, what the heck is so special about them? These two numbers, seriously, does it make sense why we do ones and zeros? Really, we should be using 0 through 9, like we do normally, because we're human beings and we like logical things. So why do we choose something that doesn't make sense to us? Well, first of all, because it's impractical. Having a lot of numbers just kind of sucks because you have to define them all in some way that can be mechanically or electrically defined. You know what's a really easy thing to define? 1 and 0 as being on and off, or true and false, or positive and negative, and etc., etc., etc. This is something that we can do electrically, in fact, with just, positive and negative, or off and on, or true and false. In fact, we've even made things that do that. For example, the transistor. The transistor, what it does is acts as an electrical valve. So, if it receives a voltage, or if we want to talk conceptually, if it receives an on or a true value, but really, in reality, it does just receive a voltage, what it'll do is it'll allow electricity through based on that voltage. So if you give it full power on that one pin that I just showed, then it'll just let everything through all the way. If you don't, if you give it nothing, then it will impede all electrical flow, or, as much as it can, really. Nothing impedes all electrical flow, but that's for electrical engineers, really, to deal with. So what that does is it just means that anything there doesn't really get through. It stops all electrical flow. Now, how is that useful? Well, we can define plus and minus, on and off, true and false, as 1 and 0. How is that useful? Well, if you arrange transistors in a specific way, you can make them do things that make sense. For example, you can make them into logic gates. So, what do logic gates do? Well, they change values, based on what they really do. A NOT gate, for example, will turn a plus voltage or a true value or a 1 into its opposite. Or, a negative or a 0 also as an opposite. So, it'll turn 1 into 0 and 0 into 1. Positive into minus, minus into positive. There are also others, such as AND, which will only put out a positive if both of its inputs are positive. Or, what you can say is what it does when it gets two ones, it only gives out a 1 if it gets two ones. Otherwise, you're screwed. NAND is really just an AND plugged into a NOT. That's literally what goes on. So it will do just the opposite. So it'll only give out a false when both of its things are true. So that is the only time when this can happen. Or only works if any of its inputs are positive. So if you have a negative and a positive, or a 1 and a 0, what you end up having is, a positive, or a 1. And the only time it's ever negative, or a 0, is if both of its inputs are negative or 0. and NOR does the exact same thing. So we're not going to discuss it that much. Now, the last thing, which is kind of interesting, is the XOR function. So, what XOR does is it only allows the signal, it only gives a positive signal if only one is positive. So, this situation can occur, and its mirror image can occur. However, if both of the inputs are positive or both of the inputs are negative, the output is negative. Or, once again, we're going to talk about with numbers, a 0. So, how the heck does this help us do math? Seriously, why does knowing these things help at all? Well, if we arrange the logic gates into bigger constructions of transistors, we get arithmetic units. So we can start doing math with logic gates. Now, what we have here is two gates, an XOR and an AND. However, what we see here is if we say that this top input right here is the first number that we're adding, and the second one is the second number that we're adding, we can start actually seeing that this will add two numbers. So, for example, say we were adding 1 to 0. Remember, we're adding in binary, so instead of going 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, we just go 0, 1, and then we start carrying it over as soon as it's anything over 0 or 1, anything over 1. So, if we're adding 1 plus 0, we get, well, 1. If we're adding 1 plus 1, then we get 2 here, but really, what that means is we carry the 2 over here, and it turns into a 1. Just like we do with regular arithmetic. So what happens here is we get a 1 and then a 0, which really equals 2. So, how does that work in our logic gate system? Well, let's imagine our numbers as these signals. So, adding a 1 to a 0 is actually really just adding a plus to a minus, right? So, we can say the 1's place is we can see that it's going to be a 1, or, just a positive, right? So, in fact, we're going to actually write these as the numbers so we can start, stop confusing ourselves. Now, these also go to the AND, which sees a 1 and a 0, which aren't the same. They're not both 1s, so it gives a 0. So thus the number that we get is 0, 1, or just 1, which is correct. Now say we're adding 1 and also 1. Well, what we can start to see is that the XOR first decides that because there are two 1s coming to it, because there's too much stuff going to it, it's going to say that we're going to let the carry bit deal with this. So we're going to give that a 0. However, the AND now sees two 1s, and, well, it gives a 1. So what we see here now is 1, 0, which is what we got here. Processor, the Intel Core i7. So, we combine more and more of these to do more and more complicated math. We can do cryptography with them. There's just so much stuff that you can do with it that really no one person can understand it all. So, the objective is not to understand it all, but to understand how to use it. So, say we do have this sort of black box, or in this case a white box, I guess, that we call the CPU. It literally just has a Memory holds two things. It holds A, your program, and B, just things that you're storing there. For example, variables. They're basically storage containers for data. For example, integers, decimal numbers, images, data, just in general. We're going to split that into two things. And really, the CPU takes programs in, and it deals with memory, just this data storage, in both directions. And again, the transfer of information here really looks like this. Just a bunch of ones and zeros, or a bunch of ons and offs. So we don't understand what those actually mean. We just know that they are a thing and that they represent something that we actually understand. And also, of course, we have other things that it deals with. For example, the input, which ranges from anything from like keyboards to motors to mice. And really, those only go in. And again, they look like a bunch of ones and zeros, so we don't really care what those ones and zeros mean, as long as we know that in the end, those ones and zeros turn into things that make sense to us. This is the way every programmer thinks, not just beginners, by the way. And finally, I have the output, which is really just same thing. Monitors, LEDs, and really motors. I don't know why I put them there, but they really should be outputs. Whereas on robots, a sensor would be the input, where you don't do anything to it, but you get data from it. So, this is the way our computer interacts with everything that's connected to it. There's a lot of stuff there. Seriously, a lot of physical stuff. And we really don't care how it deals with it in the end, as long as we understand what it does, what overall happens between one thing happening and another. For example, we know that there's only a finite number of pins on a CPU, right? There's about, 64 of them, roughly, because, every input really only deals in, 64-bit. So that means there's 64 bits being sent to it, or being sent out of it. So that means that your instructions really can't come in packages bigger than that, or if you have a smaller computer, a 32-bit computer, then it really can't be in packages larger than 32 bits. So you know that programs have to be line by line, single instructions that are really short, that do small things, but turn into larger things in the end. Your data also has to be in smaller packets. Generally, actually, what we deal with is data that's either 8 bits long, or 32, or occasionally 64 bits long. And again, this is defined by the fact that the CPU has a certain number of pins, and we understand now why those numbers are important, because that's just physically how many inputs it has. Keyboards and mice and sensors and monitors and LEDs, etc., they also receive things in smaller packages that need to be just turned into trains of packages. So now that we know why things come in these small packages, why things need to happen in order, we can start actually programming. So what we're going to do is we're actually going to have several languages that we're going to deal with. We're going to have Java, which I personally think is the easiest one. The link will be down here. In fact, we're going to just make a game. First, we're going to go over the basics, then we're just going to make a game. Next will be Python, which isn't any really more difficult, but it takes a bit more setup, and it acts a bit weird. So we're going to do that next. And we're going to do the same thing, so if you feel like, you don't need to really do the same program, you can just go over the basics and then just decide to do whatever the heck you want after that. And finally, we're going to go over C++, which is the hardest one. Again, you don't need to do these in order. If you feel like a badass, you can go straight to the C++ and just hate yourself. But I would suggest the Java. If you don't see the links yet, that means I haven't made the videos yet. Chances are the only thing you'll see here is Java, unless you're in the future, which you are. Oh my God.